Right. So today we are going to discuss in the operating system lesson the process state diagram, right? So basically we have 7 states in this process states diagram today, but we are going to look into the 5 states, right? So I'll be explaining the 5 states process diagram, right? So I wanted you guys to do with me, right? Process states diagram, right? So, for an example, now let us imagine that we have an program, right? We have a program MS Excel, right? We have a program MS Excel. Now, once you open this program MS Excel, what is actually happening? It will go to our random access memory. So actually, right? So it will go to the random access memory, and actually this is where the process gets created. This is where the process gets created. Process gets created, guys. But we imagine that suddenly when we open the program, the process gets finished. No, actually that's not the case. Our process needs to go through some states. After the process fulfill those states only, the process will get finished. And it seems for us that the process has finished, but uh, because the computer is much faster than us, but actually it's not the scenario. This is where the process is getting created and it must go through some states for the process to get finished. So let us discuss that step by step. Right. So here what I'm going to do now, so let me draw the diagram, process state diagram. So first we are going to have the new state, right? Right. We are going to have the new state. I'm going to say this as new or created. You can say new, either you can call it created. Right. Now, once you I told we imagine that the MS Excel application program is there. So once you open it, this is where the process gets created, right? So this is where the new state comes into the play, right? And after that, what will happen is, right? The main purpose of any process is to get processed, right? Is to get processed to reach the running state, but it can't go directly to the running state, right? It need to go to the ready state after getting created, right? So here we come to the ready state, right? So after it get created, right? What will happen? It will get admitted to the ready state. From the new state, it will get admitted to the ready state. So we can call this as admit. So the process where it is getting moved from the new to the ready is, we can call that as admit. Right. Now in the ready, there will be many processes, not only one processes. So there will be a queue, right? There will be a queue. Now, when you guys go to a bank to deposit cash, right? Now we imagine there is only one counter in the bank. You are not using the CDM machine. You are going to the bank physically and going to a counter, and there is a queue. The queue is long. So can you go directly to the counter person and say, look here, take me the money and deposit this cash? No. If there is a queue, then you need to wait right in the queue. So like that, this one also there is a queue. The processors will be in the queue. So directly from the created state, it can't go to the running state. It must come to the ready. Then it will go to the running state, right? So what will happen? So now I'm going to draw the running here. Right. Running state. The process where it will come from the ready to the running is called as dispatch, right? The ready state, there are many processes. So in the queue, so which process need to go to the running state? It will be decided by the operating system, whether it is based on the priority basis or maybe it is maybe based on first come first serve basis, like that, right? So we'll be studying these things in the scheduling. Right. Then after the operating system decides which process to be sent to the running state, that process will be moved from the ready to the running. Now all the processes in the ready state can't go to the running state, because we have studied only one process can be processed in the running state, right? The CPU can process only one process. So here this we moving from the ready to the running, we call this as dispatch. Dispatch, right? Dispatch, right? So now we'll imagine that the process is in the running state and it has been finishing executing, right? Actually, this is in the running state is the state where the execution, the processing is taking place. So we'll imagine that the process has finished the execution without any problems. Then it will get terminated. We call this as normal termination. Without any problems, it will get terminated. Right. I'm going to say here terminated. Right. So the process moving from the running to the terminated after getting processed, we call that as terminate. We can call that as terminate. So once the process has been finished execution, it will move from the running to the terminated state. If it doesn't meet any problems, we call this as normal termination. Right. Now, certain amount of time will be allocated for a process in the running state to get processed. If that process is taking more time than the time that is allocated for that process, we can't keep that process in the running state, right? So nicely listen to me. So there will be some time allocated for the process to get executed. But if the process is taking more time than the allocated time, we can't keep that in the running state, because we know that our running state can only process one process, right? So and other processes are waiting in the queue. So therefore we need to um, move that process from the running to the ready state back. This is because to the timeout. So we'll say this as timeout. So when a process is taking more time than the allocated time, it will be moved back to the ready state from the running state. That is timeout. Imagine a process is there and it needed the printer. For to take a print. But I will imagine the printer is not available at that moment. Then what happen is, right, the process will be moving from the running to the blocked state. Now this ready state is also in the random access memory and the running state is also in the random access memory, right? So when there are any IO device requirement and if it is not met, right, then it will be moving from the running state to the blocked state, right? So here let me draw blocked. We'll move into the blocked state. So why it moved to the block state? Because of IO event wait. Right. So that is the reason. Then now we'll imagine now it has the print is there and the IO event has completed. Then it can't move directly to the running state. I told that any process can't move directly to the running state. First, it must move to the ready state. After that, only it will move to the running state. Now, this block state is also in the random access memory. Okay. Then what will happen? It will move from the block to the ready. After that, it will move to the running. Right. Right. So here we call this as. Now, why it came from running to the block? Because of output event wait. Now, the reason why it is moving from the block to the ready, why? Because IO event completion or the IO event occurred. So here I can say IO event completed. Once it completed, it will move to the from the block state to the ready state, right? Now I know you guys will be wondering. Now you told us that before process due to when a process is taking more time than the required time, it will be moved from the running state back to the ready state. You will be asking me a question, okay, but it has not finished the execution. No? Then won't it come back again to the running state? Yes. Now again it will come back to the running state to finish its execution based on the scheduling that the operating system makes, right? So there is a queue, right? So based on that, again it will go from the ready to the running based on the operating system's scheduling. After that, it will finish the execution and get terminated, right?